Okay, so here we are. I just started recording this section, and again, as I said before, we're going to talk about a little bit about the sampling distribution and t-tests, and then we're going to talk about the central limit theorem and explore that more and really understand it using some R code that is not in the class. About 15-20 minutes. I'll go pretty quickly. Those of you who had arrived while I was working on the microphone have seen the simulation, and you'll see that when we take many samples, they characterize what we call the bell curve or the normal distribution. And as I was saying, when we talk about t-tests of means, we're really just talking about whether or not the assumed, or actually the assumed sampling distribution that is unobserved between two means is different enough that we can be confident that those are not just a fluke. And sometimes those differences can be quite small if we compare the average between one group and another, say the mean of one group and another. The practical significance can be small. That is, there's a small descriptive statistical difference. But, there's a small practical significant difference, but there can be a highly statistically significant difference, which means that we are very confident or reasonably confident that it actually exists, that difference actually exists. The example I gave before I started recording was of aspirin and heart disease. Taking an aspirin a day has been demonstrated to reduce the risk of heart disease, mostly because it actually thins out the blood. So we not only just have a test, we have a theory, we have some body of knowledge there, but that's an example where you might have statistical significance that's not based on practical significance. And as I said before, basically here on out, we're gonna focus on four kinds of inferential statistics that deal with the different kind of data types. When we talk about numerical differences, numerical data, we're talking about averages. We're going to use t-tests, but t-tests, as I said, are simply eponymous, which means they're named after Gossett or student. The person who published anonymously the behavior of the normal distribution when the sample size is small, and that means that the tails are a little bit thicker. It's just kind of the corpulent cousin of the normal distribution. We talk about proportional tests next week, which means that if you have categorical data, so you want to look at the percentage of people who die as opposed between those who take aspirin daily versus those who do not. That would be a good example of a proportional difference. And then we talk about tests of independence for contingency tables. Remember, we have those 2x2 tables or 3x2 tables. We want to know whether or not those differences are statistically significant across all groups. There's something called the chi-square distribution, or chi-square test. It just tests whether or not those groups are different beyond chance. So we're labeling different names of distributions, but they fundamentally go back to the normal distribution. Last week, we're going to combine correlation and regression. These are we're going to look at the association between two numerical data variables through correlation and regression using statistical inference, which also is actually based on the t-test for regression. The slope of the line is actually based on a t-test. Along the way, we're going to push toward you something called the F-test. That's named after R.A. Fisher. He's another statistician. These are all just different distributions. What's really cool here, which is why we should not worry about the jargon or the names too much, is that unlike many fields of science and study, statistics is still pretty unified. There's a neat article that actually tried to show this. And I'm going to show you this figure. I'm just going to share the screen. I circled it. It's basically, it hasn't been done before, but basically there are a lot of different kinds of distributions, and these are probability distributions. They describe different shapes of essentially, how do I say, different kinds of variables. So the normal distribution is the bell curve when the sample size is far above n. The chi-square distribution is kind of, it's like a teardrop. It's censored at 0. That means it stops at 0, but it goes kind of off into infinity. It has a long right tail. The f-test, can't even visualize it. And the t-test is, and then there are other kinds of tests. But the main point is they're all derivative, or they're all related to the normal distribution, which is related to this idea that when we take many random samples and we aggregate those, they have a property that is consistent, that is something that we can hang, as my grandfather used to say, we can hang our hat on it. That's notwithstanding the controversy around some of these things. I want to share this screen now, okay? And I don't want you to get lost in this. I'm going to share this to the course website, so don't worry about it. But I just want to show you just maybe how cool it is. Do you see this the screen here? This is actually a screen pick of capture of one graph in a leading statistics article that basically shows how, as they used to say about the Roman Empire, that all roads lead to Rome. Well, you can derive most distributions. In other words, no matter how complex the outcome is, we have counts, we have bimodal distributions, we have something called finite mixture models, we have something called Bayesian statistics, which is based on the idea that you have prior knowledge. It all goes back to the normal distribution. I put the circle there. And if you look at the notation here, we have the Greek notation that we use in class. So we'll use the letter N for normal, comma, mu, meaning the mean, and the sigma square, this is the variance, this is not the standard deviation. And this describes the distribution, which is a symmetric mound-shaped distribution. The L here, I think, is shorthand for some kind of, it's a linear combination. It's just basically it's this most simple foundational relationship. Now, if you just zoom out a little bit, here we see just what looks like a kind of a crazy traffic jam. But you'll see some of what we'll see here a little bit. I just want to share with you the fact that these other distributions, actually, when we visited those are just extensions of the normal distribution. So no one's going to quiz you on the chi-square distribution. But look, we do have a chi-square distribution right here. This is going to be for the week on contingency tables. When you talk about the standard normal distribution table, when we talk about z-scores, that's a little bit of a different thing, because remember the mean is 0 and the standard deviation is 1. But it's essentially a variation of this normal distribution. The t distribution, see, now if I zoom out, it'll disappear, but the t distribution is somewhere around here. Should be pretty close. Well, in any case, I'm going to share that with you. There are other kinds of chi-square distributions, something called non-central chi-square distribution. These are just little tweaks. These are ways of dealing with deviations from that normal distribution. It's sort of like, it's sort of like, how do I put it? A lot of architecture, it tries to be resilient to, say, earthquakes or movement. Well, there's this whole field called robust statistics. Robust statistics simply deals with primarily deals with deviations from that normal distribution. And we don't want to change everything. We just want to make our distribution, tweak it, and make it robust. So it's sort of like making a bridge with some buttresses. It's just so you're making it a little bit robust to deviations. And that's essentially what you have. So no matter where you go from here, you're going to have basically everything you'll need. And I'm going to share this. I'll also share that article. You don't need to read the article, but it's it's just a neat exercise that is shockingly has never been done before. So I need to erase this. So clear all. If I can, I'm sorry. Please let me know if you're picking up the sound of the vent of the computer. It sounds like the fan is on. See, I just saw t-test. Anyway, this is going to bother me because some of these seem a little bit far. There we are. There's a t-test, t-distribution right there. So there's the t and there's the n right there. So there is, and here's the f-test right here. See the f there. So we don't need to know the mapping of these associations. This was published maybe 2 or 3 years ago. It's pretty surprising it hasn't been looked at before. But the point is, when we talk about regression, we're looking at a linear outcome, a numerical outcome. Well, guess what? What if your outcome is a yes/no question? You can still do a regression just with a different distribution, and then you don't have to think about it. You can still think about it in the linear framework. So what we're teaching you is actually things you can do from here on out. Well, I'm going to debate whether or not I should do the central limit theorem, because you did see it earlier. I'm actually more inclined to actually get us into t-tests, because I want us to get started on the t-tests themselves and on the homework. If we have time, I'll do it tomorrow on the central limit theorem, because it's something we can revisit. But I think that it's important just to keep in mind when we talk about the normal distribution, it's not normative. It is not an ought statement. It is an is statement. It is, in the sense that if you talk about it is ought distinction, it's simply to describe not how things should be, but really what is. It's not a good use of a term, I don't think, but it's something that is there. The bell curve is why we often call it that too. But there's nothing normative. There's nothing normal. It's not like normal psychology and abnormal psychology. It's simply there. Okay. And everything we're doing is basically based on that. So what we're going to do when we talk about t-tests is in the homework, we basically have you go through our code, and we have you run our code that look at different kinds of t-tests. Well, what kinds of t-tests are there? Well, t-tests are tests of means. And remember, as I said, they're based on the t-distribution, which is essentially the normal distribution, assuming the small sample size. And if the sample size is large within groups, then the t-distribution behaves or approximates the normal distribution. So we just use t-tests. We're fine. There is something that you'll see in the code that is called the Welsh variance adjuster. It's an option. It's like another one of these tweaks. It's somewhere around in this Byzantine figure. Let's not concern ourselves with that. Just remember t-tests. We basically have different kinds of tests. We have tests of whether or not a mean is equal to a hypothesized value. So these are one sample t-tests, right? You have a sample, you collect your data, and then let's say I think the number of people on planet Earth are 6.5 billion people. And you collect the data, you look it up, and then you run a test comparing my hypothesized mean and then the data, and you look at that inconsistency. And that inconsistency is measured by something called a t statistic, and it'll have something called degrees of freedom, which is the n, and then notably the p-value. And if the p-value is less than 0.05, then we can say that my estimate is inconsistent with the data. that's the whole, trying to repeat the language. You with a t-test, you're having one mean value either hypothesized or in the data, and you're going to want to know whether it's consistent with another mean value or average that is in the data. It's always in the data. So in a one sample t-test, you're going to have a data point, you're going to have a mean, and you're going to say, well, I hypothesize that an average that is equal to that mean, greater than that mean, or less than that mean. You can make many different kinds of statements, whatever it is. That's a one sample t-test. In other words, you have one sample, you have one planet Earth, you have one population, and then someone throws out some crazy claim, and you're going to see whether or not their claim, assuming that they had this imaginary, this is interesting, right? Assuming they had done the test based on expertise or based on whatever, whether or not their claim is consistent with yours. Now, sometimes it'll seem quite obvious. 6.5 billion people actually is not, maybe a lot of people would think it's 6.5 billion. But if I said 1 billion people, you would know we don't have 1 billion people living on planet Earth. It's more like 7.6, 7.7. Still, whether or not I hypothesize a population, true population value mean of 1, I want to say, I'm actually using a mean here. I apologize. I could say the average number of people born per day or something like that. I apologize. I actually talked about a count here. See, this is actually a good example of how statistical tests are sometimes interchangeable. When you talk about proportions or means, you don't have a mean of a total population count. I totally apologize. We could say the average number of births in the United States might be 300,000. Now, if I said the average number of births was 12, those are two claims that are both can be tested statistically. The larger number is more likely. I actually don't know what the true value is, but if you have data, then you can do a one sample t-test, and that one sample refers to the data you collect, and you're looking at the consistency of a claim with those data. And that claim can be pretty reasonable, like 200,000, or it can be totally off, like 10 or 20. Regardless, the statistics will spit out these values and give you a p-value. That's the math. Now, what it means, though, is let's imagine you have people who are denying that there are at least 100,000, tens of thousands of people being born in the United States. Let's say you have people who deny that. Statistics is a principled argument that can still be very useful for convincing the public, convincing experts, maybe not politicians or people in power, but convincing many people that wild claims are inconsistent with the data, and you can quantify how inconsistent it is for me to claim that there are 20 people born per day, and how much more consistent it would be to have a count or a mean that is in the 20,000s. So that's the utility of statistics, even when you're testing a one sample test against a wild claim. So because it's a principled argument, you have numbers that are actually convincing, but also it shows you the degree of consistency as well as the degree of disparity. A wild claim can be shown to be outrageously off. Now, the two sample t-test is more common in my experience. Two sample t-test is essentially, we can talk about paired or unpaired, but the main point, we're going to focus on not necessarily the pairing of it. We'll just focus on the fact that when we talk about two sample t-test, think of an experiment. Think of a comparison. Think of two means, two averages. And you want to compare those two averages. So if you have an experiment, you have a treatment group, and you have a control group, right? So let's say we want to test a new medicine. You give group A, the experimental group, medicine, and you see whether or not it cures melanoma, a form of cancer. And then you have the control group, and they don't receive it. Now, of course, that's would never be possible. It breaks laws. But here you have two data points. You have a treatment and you have a control group. You have two groups that differ. That's in the experimental setting. So when you talk about a two-sample t-test, it means you have two averages you want to compare. And this is the workhorse of 99% of randomized control trials, of medicine, evidence-based medicine, of most of the data that you will get if you go to the hospital, and a doctor will tell you, well, the odds of this are likely of to be this efficacious, or this pill will this work, we think, because it's published in the medical journal. Most studies are going to use something like the t-test, which is really cool, because you're learning the statistics that is foundational in experimental psychological science and in medicine, and in the what is called the randomized controlled trial, which is simply to say you're going to take two groups of people, you're going to randomize them into the treatment or the control group, and then compare their outcomes and see whether or not the treatment works. Right? These are often, you give people an experiment, you give people a treatment and see if it works. Of course, for IRB, Institutional Review Board stuff, we'll use animals first, but what's antidepressants are very common, right? So antidepressants are based on that idea. Basically, you give one group an antidepressant, and the other group you do not, and then you look at their depression scores after some period of time, and then you run a t-test of a two-sample t-test of means. So you can look at that. I actually looked at it in my own stuff, and you can see that that's huge. So that's much more common when you look at published research. I think you're going to run into it in your own work because we have so much data, and because the foundation of the pharmaceutical industry, of experimental research, of developmental economics. A lot of economics is based on experimental data. A lot of public health interventions are based on experimental data. Now they're more complex. Sometimes there are many treatment groups, but let's take the base example. I'm using the experiment as a hook for you to remember what a two-sample t-test is, because it's easy to remember what a treatment and a control group is. Two-sample t-test, two means. But it doesn't have to be experimental data. We looked at this in the homework. You can look at, say, are Republicans, let's look at political, let's look at politics. Are women more likely to vote for a Republican presidential candidate in the United States or a Democratic candidate in the United States? So, I'm sorry, that's a proportional test. Zoot, okay. Are women more likely to attend church more often over the year than men? So if you ask men and women in the United States, and you do a sample, say we collect 1,000 people, and we ask them, how many times do you attend church? Assuming they're Christian. And we count them up, and we average within each subgroup the number of times on average they've attended church. We'll have the female, the number of times women have attended church in our sample, and the number of times men have attended church on average in our sample. Now note that I'm talking about observational data. We're looking at the mean differences between men and women within one sample that is non-experimental. We're still going to call this a two-sample t-test because we partitioned our data into two groups and we're comparing those means. So that's where the language might get a little tricky here. Two-sample t-test doesn't mean you're collecting two different samples. It means you're partitioning, you are dividing, you are splitting the sample into two distinct groups in observational data to test whether or not the averages are different between the two. And next week, we're going to look at whether or not the proportions are different between the two. As a preview, women are much or more likely on average than men to report attending church over the year. Now, there could be reporting bias, but men apparently don't go to church as often if you look at the number of counts. But that would be tested with a two-sample t-test. Two-sample because even though you have one sample, one study, one survey of randomly selected, say Christian Americans, you could say, you're still looking at a numerical count, and you're looking at how that numerical count would differ between two groups. Okay, I know I did a lot of explaining. I want to go to some code. I'm gonna make this a little more fun, I think, if you don't mind, rather than sort of give you just the homework, because I think you guys can do it. I'm gonna give you. Oh, we'll do the homework. That's fine. I was gonna say I could do something else, but I'll run you through the homework. I don't like to do the answers too much because I feel like it deprives you of that opportunity, but you're going to see me skip some of those. You're going to see me skip some of the questions and just go through the code, because I think I hope my explanation here is useful. Okay. So hold on, sorry. Just opening up the problem set. So are there any questions, by the way? Oh, I'm sorry for that. Oh, question 7 on the homework. Okay, so let's see if I can try to answer the question obliquely. I don't like to feed you answers. Do you have a question about the homework that I could try to answer in a way that is not that illustrates the concept? In other words, if you can word for me the question, not just what number it is. As I like to say, a question ends in a question mark. And in fact, that's okay. You're not sure how to interpret it. Okay. Well, let's take a look at it. So this is an interesting point. So, all right. Let's see how much time we have. We have 20 minutes left. If we run out of time, what we'll do is we'll go through the homework code tomorrow. Go through it quickly. I'll also post a video of a previous term where I go through the code itself. But I think this is an important teachable moment, because interpretation, how do you interpret a question, is the hardest thing in statistics. The data are there already. The computer programs will give you the data. What we desperately need are good questions, and we need good understanding of those questions. If you could speed it up for me, would you be able to copy and paste the verbatim question? Otherwise, I'm gonna hunt for it. I don't want to waste time, unless I'm looking at it. Okay. So the question is, how do you interpret it, because it does not give you anything to calculate? What if there's nothing to calculate? Well, I'll look for it. But while we're doing that, I do want to, just at least since we're doing more of a conceptual review, I'm going to share the slides. Wait, do I have the homework here? I should have the homework here. Ah. Sorry, I actually, for some reason, I don't have the actual homework here. I just wasn't, but I'll grab it. Any other questions about t-tests, about perhaps my disquisition on this? All right, so the question here is, thank you for asking, but if you have any other questions about this, I'm going to stop my share, and I'll do a new share. Because I think there's a lot of stuff this week about, probability and type 1 and type 2 errors and all that kind of stuff. But I do want to go to just the idea of the main concepts here, which is this. You have an approximation of the normal distribution, and then you have basically z-tests and z-intervals, t-tests and t-intervals. These are for comparing different values. These are for the actual tests. When we do the code, we actually have 2 sample t-tests. So let's take a look at the question for number 7, and I'll look for it as well. Where was that? Sorry. Thank you. Too many windows open. Suppose you took many samples of 10 people from the population. Okay, so we have a population, unobserved population. That's a capital N, and we take many samples. Already I'm thinking of a sampling distribution. Comma, suppose you take many samples of 10 people from the population, each time calculating a different sample mean for age. Okay, so here we are taking a sample, 10 people from the populations. Say we take Americans, we grab 10 people out of the sample, and then we have a mean, and then we calculate a different sample mean for age. What is the average of these? Okay, there's some type of what each time calculating a different sample mean for age. So in other words, you're having what is called an X bar, right? You're having a different sample mean each time. We don't know how many of these 10 samples we're doing. That's why I showed you at the video at the beginning. You kind of increase it, you're going to get that normal distribution. It'll be a t-distribution when it's smaller, or when the n is smaller as well. Then it asks, what is the average of these sample means? Okay, is that a write-in question or is it multiple choice? Because this is what this question, I can tell you, emphasize. I'm gonna have to look at this, and if I don't answer immediately, I will. Yeah, it is multiple choice. That makes sense because there's no numeric answer you can calculate. It's conceptual. So I'm gonna bring it up, but the point here is, of course you can't calculate it because what is many? Someone asked Abraham Lincoln, the president, the tallest U.S. president, how tall must a man be? He said tall enough for his feet to reach the ground. How many samples must you collect until you have an average that is approximate to the population? Okay, that depends. Okay, so it looks like the questions here are quite specific. There are 4 numbers here. I believe this is a follow-up to a previous question that gives us information. And this is something I talked about when we talked about the midterm and in the homework assignments as well. Sometimes the information is not isolated in each particular question, right? Because if you look at the R outputs, or if you look at the, especially the part 2, or I think it's typically part 2, when we look at the R code, we're going to ask you a question using the same data set. We're going to look at another aspect of the data set, and you're collecting that information. So this is like the real world. You have additional information that is not isolated from each question. That wasn't for the midterm. That was actually for for the homework assignments. So I believe there's information external to that question. By itself, you can't just get an answer, but I'm gonna look at this, okay? So please bear with me while I'm getting the problem set. Gosh, if I don't, okay, here we are. Good. Okay. Sorry, I should always bring this up. Okay. So let's take a look at that question. So suppose you take many samples. Sorry, I'm looking for the question. Is this drawn from the code, or I'll have to get back to you on that. I believe that could be from the actual code itself, because we do have you sample at different numbers, right? And we do have you round to 2 decimal places. I'm actually not finding it. And I don't want to use up just dead air time. Because what we do have is with the R code, you actually work with the t-distribution model, right? So you can basically create plots of the sampling of the standard normal distribution model based on samples 4, 10, 50, and we ask, does the shape change? And no, the answer is the shape of the distribution does not change as the sample size increases. But that's more about the t-distribution. I'm not sure where that's coming from, and I apologize. I'll get back to you on that. I don't want to distract from the actual lesson itself, but I'll look at that. Yeah. Oh, well, thank you for your kindness. The student said, no worries. I'm more worried because I should know this. It's the pedagogical reason, and I'm probably just not finding it, and I don't want to waste time finding it. Anyway, here's the point. Okay, so remember we talked about t-tests. We talked about the t-distribution model. And we reviewed this. Remember last week we talked about estimation and hypothesis testing. A point estimate is what we're going to call proportions. We're going to call it means. Point estimate is just a new way of reframing what we would call a mean in descriptive statistics, because a point estimate is a little point on a range of plausible values within that confidence interval, because it's measured with uncertainty. This is why I'm talking about anti-precision. One little parlor trick I do is I If I want to impress students, I'll go and I will pretend to know pi to 40 digits, and people will think you know it, but I don't know it because it doesn't matter. No offense to those who do. It matters for certain things, but not in statistics, because the point estimate is a noisy little jumpy thing. It's within the confidence interval. It's a little point we have there, and the 95% confidence interval is the range of uncertainty. If we think about 95% confidence intervals, you'll see it in weather patterns. Last September, my mother lived in Florida. We had a hurricane prognostications. You saw this cone of uncertainty, these fanning like red paths. That's a way to think about a confidence interval. You don't know exactly where the hurricane will go. You don't know exactly where the true population average lies, but you got your best guess, and you got that confidence interval based on the central limit theorem. We're talking about one sample t-tests, and with small samples, the tails are fatter. And one thing I didn't emphasize as much was this idea of I suppose a z-test. It's not in the homework, but the point of a z-test is essentially the same. You're using the same distribution, but I would actually you're using the same distribution, because a t-distribution and a normal distribution reach the bell shape at large enough sample sizes. But let me see. I want to show you what the standard normal distribution will look like, and what the t-distribution will look like at certain ends. And we'll do that. We won't actually do the t-tests of differences between groups and t-tests vis-a-vis a hypothesized population, like your best guess, although those are in the R code. But I do want to do that for the last 10 minutes because it's important to understand. Before we do that, I do want to show you this slide. I think I'm sharing this. This is something you should thumbnail. I don't like it because science is more iterative, but you need to know this. Science is typically, you look at the data, you have a hunch, you'll look at things, it's more circular, it's more intuitive. But remember these 5 steps. You're going to state the null and alternative hypotheses. You compute the alpha level. It's going to be 0.05 typically. You compute the z-test statistic or the t-test statistic if the sample size is small, but same thing. It's just a number that describes how far your estimates are. And then you're going to assume the null is true, and then you're going to look at the p-value. And if the p-value is less than 0.05, it's statistically significant, and you conclude, say whether something is right or wrong. And we're going to go through those examples tomorrow. But you should remember this. I'm going to flag it. It's 38. Just practice it aloud, work on it, and we're going to go through that tomorrow step by step. I know it's a little rote, but I do, gosh, we're running out of time. I'm going to go about 5 minutes over just because I want to show that R code and show you what kind of cool stuff you can do with test for means using the data set at hand. Just in case, for those of you maybe who, I don't know, are having trouble with the data set, or you haven't looked at it yet. It's a really cool data set. It's called the American Community Survey. Those of you who are undergraduates, in particular, I encourage you to look at this data set. It has 10 observations. This is actually the government data set. It is the long form of the U.S. Census, which is in the news now because they want to ask a question about citizenship. The census, of course, asks a question for everybody. The American Community Survey asks more questions with a smaller sample of the population. It's a random sample. I actually filled it out. It's like a big pack. It was like filling out your taxes. But the sample that we have in our data set, and I'm going to stop the share because I realize I need to share it again. The American Community Survey has a lot of variables, but the N, or the sample size, is a little bit smaller than what it really is. It's still like in tens of thousands. So here we are in our console. I just loaded this American Community Survey data set. This is from what we have here. But I encourage you to look at this for class, because you can look at many different kinds of tests. We have categorical, numeric variables, things like that. I'm going to open the code, and just to make sure that you're able to do that. Come on. I'm going to. Sorry. Sometimes your default might be R rather than RStudio. So just make sure your default is going to open in RStudio. Okay, here we are. You'll see me messing around with some stuff here. If you look at this code here, I just want to show what this plot dist function. Oh shoot! And because of updates, we may run into problems with this. I realize, because I just installed the newest version of Mosaic. I'm going to install these packages. So we're going to go type Mosaic here. This is one way to install load packages once they're installed. Yeah, it should be fine. Okay, you know what? Just to be careful, I'm going to type in library Mosaic. It's complaining because I clicked on Mosaic data. I just want to make sure I got everything installed, and we're fine. Let's see if this plot dist function is going to be messy. Oh, okay, it's good. Okay, if we look at this, I just ran these three right here. This is the normal distribution, right? It's the nice bell curve we have here, but our sample size changed. Do you see any difference here? No. Well, then that's the problem, right? Because if we have a small sample size, what happens is we can't apply the normal distribution. We're actually, it's less certain. The smaller the sample size, if you have 30 batches of beer that you're producing that day and you want to compare it to the next day, you can't apply the normal distribution. You got to make those tails a little bit fatter. And I guess that's a little bit fatter. The scale changes, but that's what we have here. So there's the, that is the t distribution with 49, and here's, oh, we should do smaller ends, I'm sorry. I'm going to clear all of these, because remember, above around sample size 30, the t distribution and the normal distribution converge. So there's the normal distribution. This is before Gossett published his famous piece. And look at that. There's that t distribution. And there here you see a 0, 5, and -5. 5 isn't even on the normal distribution spectrum. So it looks a little different because the x-axis scaling is different. But the main point is your estimates are going to be way off, and they're actually less precise. You're going to be overconfident in your estimate when your sample size is small. And that's the innovation of the t distribution. And that's why we always assume the t distribution. And this right here, this is actually the just the normal probability distribution. If you look at line 77, there's some code there that says regardless of blah, blah, blah. Remember, don't worry about that. Just keep in mind, when we talk about probability distributions, that's what it is. When we talk about distributions, it's a probability distribution. It's like it's a game of chance. So imagine you're going to throw a, oh, I don't know. Imagine if you're going to like guess, there's a thing called a quincunx. If you go to the Museum of Science, I can show it. I'll show it tomorrow. But imagine you're just going to drop a ball here. I'll show you. It came from an old game called a quincunx, which is basically you drop these balls and they'll shape the. If you ever look at Plinko, there's a American game show where you kind of drop a little token and it'll bounce around. So if you drop something from here, that's my sound effect. It'll knock around. If you drop something from the middle, it'll have an equal probability of falling somewhere. What are the odds that your whatever item you're going to fall, whatever subject you're going to draw, card you're going to draw, marble you're going to pull out of a jar, where is it going to be? Odds are it's going to be in the green zone, much less likely to be in the blue zone, much less likely to be in the red zone. This green zone is our 95% confidence interval. So that's what we talk about when we talk about sampling distributions. We're actually also talking about probability distributions, because you don't observe a probability, you don't observe sampling distributions. You only have one world, you only have enough money for one study, if that. And this p-values and probability, it's a way of thinking. It's an idea that did not always exist and was very controversial. But it started with games of chance. It started with the French. That's why I started with some nice French music, because they actually invented demoivre and came up with this concept from jeu d'hasard, or games of hazard, games of chance. And it's funny because you can call it gambling in English, but if you say it's risky, you'll say chanceux. It's chancy. That word chancy. There's where it lies, where inferential statistics lies. You get your best guess, your best data. You principally kind of make a bet, really. And in that sense, we're all kind of gambling. We're making our best guess. But the 95% confidence interval is illustrated by this normal distribution. And just think, okay, if you're going to make a guess, where do you think your ball is most likely going to hit? It's going to hit right here. Anyway, I think I've pontificated enough. It's 6:06. Tomorrow, we're going to go through the FAF stats. We're going to actually look at the data. We're going to do a t-test. This is a one-sample t-test. We'll graph the probability distribution of that t-test just so you can visualize it. We'll look at quantiles, which looks at something above or below. Remember, I said you can, with a one-sample t-test, you can say, does our mean equal something? Is it above or below something? What's the probability it's above something? What's the probability it's below something? And then we're going to do these two-sided hypothesis tests. Almost all tests are two-sided. I do have to say they're also one-sided hypothesis tests. But this is going to be whether or not our mean is equal to mu of 0. Remember, mu is the population mean. So we're going to say, is the number of hours of week equal to this value? Is it greater or less than that value? And then we're going to go to confidence intervals. I thought we had two sample t-tests here. Well, if not, that's what we're going to do next week. See, okay, well, two sample t-tests we're not necessarily going to do, I guess, this week, but we are going to do confidence intervals. I apologize for that, but two sample t-tests they weren't in the lectures, but the code right here, this code right here, is in the homework assignment. It is downloadable. You go to that part of the homework assignments. You can download the data set. You can download the code. Go to someone had asked this. We have made it so it's modular in the sense that it's what you do. It's cookie cutter. Each week you're doing the same thing. If you're running into difficulties, look at the first week on the our tutorials page. There, if you look at like the second or third tutorial, you should be able to download the code and the data set. If it's not available, that's an issue with Canvas, and we'll get to it right as soon as we close this up. Is anyone else having issue downloading the code, or has anyone tried? I'll verify it, because the code's all there. Okay. Anyway, So we will look at those confidence intervals. We'll look at t-tests. I wish we did t-tests, two-sample t-tests, but we're going to look mostly at these. We might do a little bit of two-sample t-test because it's so important. Yeah, please check and let me know. Thank you so much, everyone. And I'll also share that amazingly complex figure of the normal distribution. I hope it gives you a handle on some of this stuff. Don't worry about it too much in terms of the difficulty of this material. We're going to review it each week. That's why I want to revisit the central limit theorem, the normal distribution, and show new concepts and new ways of thinking about it. Students have told me the second half of the course is a little bit more difficult, but I just want to emphasize it's the same thing over and over again. So it's just that beautiful bell curve. All right, thank you so much, and have a wonderful Monday. Thank you so much, and I'll post this ASAP. Cheers. Take care. Have a great day, everyone.